All right, what's up everybody? So today we're talking about summation formulae. And yes, I spell it with an A-E instead of a formulas or something like that. I don't know, it's just one of my quirks. So what are the common summation formulas that you should kind of expect and get comfortable with, okay? The weirdest one, honestly, is probably the first one, where I'm gonna give you some constant, I don't know what it is, I'm just gonna give it a name, C, I'll call it C. And I want to say, what is the sum of C from k equals 1 up to n? And it's very easy to just be like, well, there is no k here, so therefore the answer is just C, right? And the answer is, well, no, that's not the case. You have to go back and say, what is the sigma notation actually saying? It's saying k is equal to 1. Plug it in. There's nothing to plug in. What's your answer? I get C. Okay, so this is going to be the first term is C. And then now k moves to 2. I plug in k is 2. There's nothing to plug in, but what's my answer? C again, and so on, until I have this list of C plus C plus C plus C all the way to the end. Now, how many of them do I have? Well, this was my k equals 1, k equals 2, k equals 3, up to k equals n. So I've got 1, 2, 3, 4, up to n of them. And so what is C added? What are n copies of C added together? This is just n times C. Okay, if you don't like that, then think about it just in concrete terms. Choose your favorite constant. So let's say, I don't know, 7, whatever. Okay, so 7. And if I take 7 plus 7 plus 7 plus 7, just like I have here, C plus C plus C plus C, what is that really? Well, that's really just 4 times 7. So that's going to be 28. Okay, it's the same thing that we have here. All right, this is probably the number one thing that trips people up, is that if I just add a constant to itself a certain number of times, what do I get? That's what you get. Okay, now what about this one? This one is k is 1, and then I move it, k is 2, k is 3, k is 4, and so on, all the way up to k is equal to n, okay? Now there's a very nice concrete formula for this. This is actually equal to n times n plus 1 all over 2, okay? Now, why does that at least make sense that it's going to depend on n, okay? Number one, look, if n were 3, I would say 1 plus 2 plus 3. Fine, that would give me an answer. If n were 4, that would give me 1 plus 2 plus 3 plus 4, a different answer. If n is 5, I get a different answer. If n is 6, a different answer. So it makes sense that the answer should depend on n. Okay, so that at least makes sense. Okay, why is it n plus 1 over 2? We'll get there, okay? We'll get there. I'm actually going to derive this at the end of this video. And I'm going to derive it in the way, not in the typical way that it's derived, but I'm going to derive it in the way that will generalize to higher and higher power. So if you wanted to say, what happens if I sum like k to the 10th power from 1 to n? How would I do that? And I'll show you how you can actually get at that formula relatively nicely, okay? Relatively nicely. Okay, so again, this one is what? K is 1, so I get 1 squared, plus k is 2, 2 squared, k is 3, 3 squared, and so on, up to n squared, okay? Now this one just has a random formula, so this is just n plus 1 times 2n plus 1 all over 6. And it's kind of like, well, okay. I mean, this one kind of freaks me out a little bit, because it's like I'm dividing by 6. Why isn't this a fraction on the right-hand side? It shouldn't be, because I'm just adding integers together, so that should be an integer. So why is this like not like 7 over 6 or something like that, right? So that's kind of weird, and you have to flesh that out. This one makes a little bit more sense, because look, if n is, say, 3, well then 3 plus 1 is divisible by 2, so that part will collapse to be an integer. But if n is like 4, then n over 2 would collapse to be an integer. So if n is even, n over 2 is an integer. If n is odd, n plus 1 over 2 is an integer. So this will always be an integer, but this one's a little bit harder to see that, okay? So if we wanted to kind of check that this is actually valid, okay, let's just do like a very small case. Okay, so n is equal to 3. If n is equal to 3 and I look at this sum, I'm only looking at this part of the sum. So that's 1 plus 2 plus 3, so that's what, 6? So I get 6 on the left-hand side. Let's just do that here. But if n is 3, what do I get? I get 3 times 3 plus 1 is 4 all over 2. That's 12 over 2, which is, well, that's convenient. It's the right answer. Okay? Well, what if n is equal to 4? right? What if n is equal to 4? So if I took an extra term here, what do I get? Well, if this is 6, then adding 4 is just going to give me 10 on that side. Okay, well if n is 4, I'm going to get 4 times 5 over 2, which is 20 over 2, which is, well, there might be something to this. Okay? Now, this isn't a proof. I've shown that for 2 values of n, this formula is correct. You'd actually have to prove this, okay? But it at least lends like evidence to suggest that this is potentially true, okay? Now let's check the one down here. So if n is equal, let's just do the same values. So let's do, if n is equal to 3, okay, if n is equal to 3, I'm looking at these 3 terms. So that's 1 plus 4 plus 9. So that's 10 and 4, that's 14. Okay, so I get 14. Oh boy, what am I going to get here? So I'm going to get 3 times 4 times, what is that, 6, 7? All over 6, okay. Well, I'm gonna cancel first to make things a little bit nicer. Like a 3 and a 6, right? So that 3 can cancel, now that's a 2. And then the 4 and the 2, that can cancel, and that's a 2. So 2 times 7 is, well, how about that? It's 14. Okay, well, let's do one more. So n is equal to 4. If n is equal to 4, all I do is I grab the next term here, which is a 4 squared, okay? So that's going to be 16, and 16 plus 14, that is 30? That's 30. Okay, so let's see what happens here. N is equal to 4, I'm going to get 4 times 5 times 2 times 4 is 8, plus 1 is 9, all over 6 again. Okay, so let's see. The 6, I'm really going to write like this. I'm going to write as 2 times 3, because I'm going to say 4 divided by 2, the 2 cancels and makes that a 2. The 3 cancels that and makes that a 3. So now I'm looking at 2 times 3 is 6, times 5, that's, well, 30. How about that? Okay, so it actually seems to suggest that this formula might actually be correct as well. Okay, so these are some of the standard formula that you would need to know, all right? But let's derive this one, okay? Let's derive this one, and let me show you how to do this. So we need to use the telescoping sums that we've done in a previous video, okay? So let me just derive this really quickly, so you can see that it's actually valid, okay? All right, so here's the derivation. Okay, if you want to call this a proof, if you want to call, I don't know what you want to call it, okay, at the end of the day. People tend to get a little freaked out with proofs because they're kind of scary. But I want to give you kind of a method for computing these things, okay? So we're going to look at a telescoping sum. We're going to look at the following sum. K is equal to 1 up to n, okay, of, I'm going to say k plus 1 squared, and I'm going to subtract off k squared. And I'm going to compute this in 2 ways, okay? I'm going to compute this in 2 ways. One, I'm going to recognize this as a telescoping sum, and I'm going to evaluate it as a telescoping sum. And number 2, I'm going to just compute this, simplify this out, and then use properties of sums to evaluate it. Okay, so method 1. Okay, method 1. So let's call this thing, I don't know what we want to call this. Let's call this x is equal to that, okay? So method 1, we're simply just going to expand out. So I'm going to say k equals 1 up to n of what? K plus 1 squared, I got to FOIL it out. So this is k squared plus 2k plus 1. And then I'm going to subtract k squared. Okay, so that cancels the k squared. So I'm left with the sum, k equals 1 up to n of 2k plus 1. Okay? Now, remember properties of sums, I can then kind of distribute the sigma. So this becomes what? 2 sum k equals 1 to n of k plus the sum k equals 1 up to n of 1. Well, remember we had a formula for adding constants. I'm adding 1 plus 1 plus 1 plus 1 plus 1. I've got n of them. So this whole thing is just equal to n. So this whole entire thing is 2 times the thing I'm interested in, okay? That's the thing that I'm trying to find a formula for. So the summation of k equals 1 up to n plus n, okay? Where this is just by itself. So that's method one. Okay, so that's what x is equal to. So this is equal to x, remember? That's the label that we gave it. X is equal to this sum. Okay, so I can say that this whole thing equals x if I want to. So I'm going to put that up here. I'm just going to hold on to that, and we'll come back to that a little bit later. Okay, so we're going to say that x is equal to this term here, 2 sum k equals 1 to n of k, and then that's just by itself plus n. That's what x is. Okay? Now, method two. Method two. Here's what we get. So method number two. If I write this out as the sum k goes from 1 up to n of k plus 1 squared minus k squared, and I just expand it out, okay? What do I get? Well, if k is 1, I'm going to get 2 squared minus 1 squared plus 3 squared minus 2 squared plus 4 squared minus 3 squared plus, what's my last term? Well, that's one n, so I get n plus 1 squared minus n squared. So I'm going to get n plus 1 squared minus n squared. And I recognize it as a telescoping sum, okay? How do I see the cancellations? I see that cancels this, that cancels this, that will cancel this, and what do I see? That will cancel this. So what are the only terms that survive? The only terms that survive are minus 1 squared, so that's minus 1, plus n plus 1 squared. That's it. But remember, this is what we called x, okay? So computing x one way, we got that it was equal to this. Computing x the other way, we got that it was equal to this. Which means that, so therefore, we're guaranteed that the formula that we just found, which is this thing, we must have that 2 times the sum k goes from 1 to n of k, okay, plus n, must equal this thing that we just computed. So that's equal to n plus 1 squared minus 1. Let me switch the orders around. Okay? And now that's beautiful, because now just think about it in terms of algebra. This is the thing we're trying to solve for. So think of this as a variable, quote unquote variable, and just get everything to the other side. Just isolate this one variable. So I'm going to subtract n over. So I'm going to get 2, the sum, k goes from 1 to n of k, equals what? I get n plus 1 squared minus 1 minus n. Here's going to be a really quick trick, okay? Now, yes, you could FOIL out the n plus 1 squared, you could combine, collect terms, cancel, blah, 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 all the stuff. Here's what I'm going to do, okay? I'm going to write this as n plus 1 squared minus n plus 1, right? If I factor a negative out of both of these terms, if I factor that negative in, okay, this is just a good general rule and like just kind of general advice, is that if I claim that this is an inequality, I should be able to justify what I did from this side to that side to actually get this and reverse engineer it. So if I distribute the negative into both sides, I get a negative n minus 1. That's exactly what I get here. Okay? But now I notice, look, these two terms are the same, so I can factor those out. So I'm left with an n plus 1 times what? Okay? Well, I'm going to need another n plus 1, but then I'm going to need a minus 1 on that side of things. Okay? Again, check. If I take n plus 1 times n plus 1, I get n plus 1 squared. N plus 1 times negative 1, I get minus n plus 1. So that checks out. And now simplify the inside. This is just n. So at the end of the day, what do we have? This whole thing, I get 2 times the sum of k. K equals 1 up to n is equal to n times n plus 1. And all I have to do is divide both sides by 2. So divide by 2, and I get the formula that we stated at the very beginning, which was n plus 1 all over 2. Okay? So there's a derivation of it. Do you need to know that? Probably not going to help you in your day-to-day. Might help you in a math class, but that's a way of generating this particular formula, is you look at these types of telescoping sums. So for example, if I wanted to get the summation of k squared now, what would I do? I'd go back to the same thing, except these wouldn't be squares, these would be cubes. If I wanted the summation for k cubed, I'd go to the same place and replace those with 4s. Things like that. Okay? All right, if you like this video or you want to see other types of derivations of formulas like this or other types of summation formulas that we've used, please comment down below. Again, like, subscribe, all the good things, and we'll keep going.